fusion fuel could start out as a cool pellet or as a hot plasma. Either way, at the start, there are no fusion reactions happening in the core. In the scientific field of fusion, ignition is the idea that fusion fuel has been heated to the point where some fusion reactions start happening. There are a number of methods that could be used to heat and ignite the fusion fuel. Because of time, I can't review all of them. There are two major options. Using lasers is the first option. It is obvious. Using electric, magnetic, and gravitational fields to compress the fuel is the other major option. That option is not so obvious. Ignition speed is important. Fusion researchers have developed methods that are fast and extremely fast. With superior confinement, slow ignition is also possible. Sometimes fusion researchers try to confine the fusion plasma. Sometimes they don't, which is, in my opinion, foolish. As you'll see, my method of confinement is what makes all of this revolutionary and exciting. It is what will change the world. Let's look at some examples. First, extremely high-powered lasers could be used to blast a fusion fuel pellet. This type of ignition, extremely fast ignition, relies on lasers only. Fusion researchers sometimes call this inertial confinement, but really there's no confinement method used with this ignition technique. Inertial confinement should really be called inertial ignition. This type of device does not use any electric, magnetic, or gravitational confinement fields. With this technique, the shape of these pellets is usually spherical or cylindrical. Keep in mind, extremely high-power lasers are extremely expensive. This is the type of lasers being used at the National Ignition Facility. This national lab is often called NIF. As an analogy, this ignition technique is like putting a pile of gunpowder on the sidewalk and then smacking it with a sledgehammer. Second, instead of just using extremely high-power lasers, less expensive high-power lasers are used in conjunction with a spherical confinement field. This is also a fast ignition method, but not extremely fast. Thus, it is much cheaper. With this technique, the lasers ignite the spherical fusion fuel pellets. Then, the spherical confinement field dramatically increases the fusion burn times. This is the hybrid system that I would like to test. This is why I want to build my own fusion energy laboratory. Unfortunately, as of this time, this technique has never been tested by any university or national lab. With regard to this area of research, they have let the United States down. Again, these high-power lasers would be an ordinary type. These lasers would not have record-breaking power. They would not be ultra-expensive. While these high-power lasers will act fast, they will not be extremely fast. As an analogy, this would be like putting a firecracker on the sidewalk and smacking it with a regular hammer instead of with a sledgehammer. Third, a preheated fusion fuel plasma is placed inside of a spherical confinement field. Then, medium-powered lasers are used to heat the plasma at a relatively slow pace. This technique will work if a spherical confinement field is holding the plasma in place ahead of time. This is a very promising technique. Unfortunately, this technique has never been tested. Unfortunately, our national research labs and fusion research facilities at universities have also let us down in this area of fusion research. This technique will require high-quality confinement fields. The cost of the laser system would be much lower, but the cost of the confinement system would be somewhat higher. As an analogy, this would be like putting a firecracker on the sidewalk, piling some metal weights on top of it, and then jumping on top of the pile of weights. Finally, my fusion patent describes a variety of other alternative methods for igniting the fusion fuel. However, they all include a spherical containment field. For example, one method works like the wire implosion cage in Sandia's Z-pinch device, except that it is spherical. If you are interested in this, then you might want to read about these other methods in my patent. Earlier I showed this graphic. It is from my patent. In this graphic you can see lasers pointing to the focal point of the core. In this graphic, a spherical fusion fuel pellet is held at the focal point of the core. When the lasers are fired, the beams pass through laser ports and hit the pellet. The energy from the lasers transforms the fusion fuel pellet into a hot plasma that is imploding. Here is another possibility. With this method, a confinement field is created over the core. Then a hot plasma is injected into the confinement field. The confinement field holds the hot plasma in place. Next, medium power lasers are fired at the plasma to heat it up further using short pulses. The plasma starts absorbing energy. At some point, the plasma is hot enough that the fusion reactions start happening and the plasma starts pulsing. To recap, with the first method, the extremely expensive technique, extremely powerful lasers are used to implode the fuel extremely fast. With the second method, less expensive high-power lasers are used in combination with a spherical confinement field. With this method, the rate of heating is fast, but not extremely fast. With this method, the laser system is still expensive, but not extremely expensive. Third, a hot fusion fuel plasma is heated with medium power lasers at a much slower rate. Finally, there are a number of other techniques that could be used to heat the fusion fuel plasma. Keep in mind, my new technique of using a spherical confinement field can be used with all of these methods of heating, including the first one, including extremely fast ignition. The heating can be accomplished extremely fast, or slowly. No matter how the fusion fuel is heated, at some point the plasma becomes hot enough and the fusion fuel ignites with a fusion burn. At first, before the fusion burn starts, the hot plasma is compressing. It is imploding. Then, fusion reactions start happening. As the fusion reactions release massive amounts of energy, the plasma will start to explode outwards. However, if it is strong enough, the confinement field can slow this expansion. If strong enough, the confinement field can stop the expansion of the plasma. If strong enough, the confinement field can reverse the plasma's expansion. The expansion of the plasma can be slowed, stopped, and reversed. If it is strong enough, then the confinement field will push the plasma back inwards. At this point, I predict the plasma will start pulsating in and out. In this animation, the inner sphere is the pulsating plasma, and the outer sphere is the containment field. I have depicted the outer sphere with three colors, magenta, blue, and green, to represent the three fields in the containment field, electric, magnetic, and gravitational. Remember, in a tokamak, when a fusion reaction pulses outward, the cooler surrounding plasma cannot contain the hotter exploding plasma. That is not the case here. Here, we've created the spherical electromagnetic field ahead of time for the purpose of containing the hot plasma. As I just mentioned, the expansion of the plasma can be slowed, stopped, and reversed. At least that is my goal. I can't wait to see this experiment done in my fusion energy lab. It is likely in the first experiment, the experiment that will work toward extended burn times, the plasma will only be slowed. The burn times will be longer because the expanding plasma is slowed. Later, in the experiment that will attempt to reach break-even, it is likely the stronger containment circuit will stop the expanding plasma. It may take a number of attempts. However, I predict it will not take too many attempts to make the plasma pulsate. Later, in the 3 demo power plants That will be a goal. The expansion of the plasma will be slowed, stopped, and reversed. The plasma should pulsate. In order to reverse the direction of the exploding plasma, the confinement field will need to be very strong. The details of this one aspect will be analyzed from every direction. My engineers will perform sizing experiments, analyze all the numbers for each class of power plant, and design the power plant so it has a corresponding containment field that is strong enough for its power rating. A commercial fusion power plant can be successfully designed even if the plasma does not pulsate. However, it will be far better if this can be achieved. Let's look at a pulsating plasma. The plasma is hotter when it is small and cooler when it is large. By the way, this explains the supposedly mysterious detail in regards to a type of star called a Cepheid variable. Now, I must take a moment and talk about a powerful crushing force that is taking place in this process. This powerful crushing force is critical. It is not hypothetical. It is real. This force exists in every wire that has current flowing through it. However, the strength of this force is not always powerful. When any current flows along any wire, it produces a force that points to the center of the wire. This force crushes the wire. All conductors experience this force. You will never guess what physicists use to describe this force. This force is described by the Poynting vector. In most cases, because the currents that are involved are small, this force is small. In electrical engineering, this force can usually be ignored. Sometimes this force becomes a nuisance. Sometimes it causes many problems. It can do nasty things when lightning strikes. In extreme cases, this force creates tons of pressure on the wire. If you suddenly apply tons of pressure to a wire, it can do some amazing things. Wires can literally vaporize and explode instantly. This force plays an important role when a wire shorts out. When a thin wire has a current flow through it, if the current is small enough, then the wire is safe. However, if a powerful spike of current flows through the wire, then this crushing force will crush the wire at its weakest point. The wire will short out at that point. The force heats and vaporizes the wire. This is a huge topic. You may wish to study what is called the exploding wire phenomenon. In my fusion power plant designs, a powerful current will flow over the conducting spheres. Again, a very powerful current. These powerful currents create tremendous crushing forces. This force crushes the spheres.